Hello everyone. In the series of videos related to the chapter electric charges and fields, today we will be discussing about continuous charge distribution and electric field lines. Continuous charge distribution. Now, what do we understand by this term continuous charge distribution? In our previous discussion on properties of charge, we have said that charge is an integral multiple of basic unit of charge, that is total charge Q is equal to N into E. That is, charge always exists as integral multiple of basic unit of charge, that is E, which means that charge distribution is always discrete in nature, right? There is one charge, there are two charges, there are three charges, so it is discrete in nature. Then what do we understand by continuous charge distribution? Continuous charge distribution is actually a system in which the charge is uniformly distributed over the conductor. Now, what do we understand by uniformly distribution of charge over the conductor? It means that the charges which are present over the conductor, they are infinite in number and they have very small space between them, which means to say that the charges are so closely packed that we consider their distribution to be continuous. Now, when we are talking about continuous charge distribution, at no time we are saying that the charge has lost its discrete nature. No, charge is still discrete in nature, but they are infinite in number, and the distribution over the conductor, whether it is a linear conductor or there is some sort of a membrane, right? So, or there is some sort of a cube, okay? So, whatever the conductor is, we are talking about the distribution of charge to be continuous. It means that the charges are so closely packed to each other that there is hardly any space between them, and we consider their distribution to be sort of continuous. That is what is the meaning of continuous charge distribution. At no time the charge has lost its discrete nature. So, first of all, we should be clear about it. Now, there are three types of continuous charge distribution. One is linear charge distribution, where the charge is distributed, as you can see, over a line, right, where the charge is distributed over a line or the circumference of a circle. In that case, surface charge distribution, where the charge is distributed, it can be a tabletop, it can be some membrane. So, there the charge is distributed over some area. And volume charge distribution, where the charge is distributed over a volume. That means it can be a cube, it can be a sphere. So, these are the three different continuous charge distributions. Now, first of all, we will talk about linear charge distribution. So, what do we understand by linear charge distribution? When I told just now, I told you that the charge, when it is distributed over a line, it can be a straight line, it can be a curved line, right? It can be the circumference of a circle. So, it can be anything. It can be a circumference of the circle, it can be a straight line, it can be a curved line, anything. So, that is, the charge is distributed uniformly over the entire line. So, as you can see over here, we have considered a line L, and the charge you can see is distributed, the positive charges are distributed over the complete line. Now, when we are talking about linear charge distribution, we define a term which is called linear charge density, and we denote this term by lambda. We denote this term by lambda. Now this lambda is linear charge density and it is defined as charge per unit length, right, charge per unit length. So suppose in this particular line of charge, I consider a small element whose length is, let's say, dl, right. Now if the length is dl, then there is a small amount of charge which will be present over this small element dl, right. So let's say the amount of charge which is present is dq. So linear charge distribution is actually charge per unit length. It can be dq by dl, right, if we consider that small line element. If we consider the entire line, then the line length is L, and if I say that the entire charge which is distributed is Q, then in that case Q by L will be called as your lambda, that is your linear charge distribution. Okay. What will be the unit of linear charge distribution? Charge is measured in terms of coulomb and meter is the unit for length. So coulomb per meter will be the unit for linear charge density. Now electric field due to the line distribution, line charge distribution at the location of the charge Q0. So suppose I want to find out what is the electric field at the point over here, where at the point where a charge Q0, the test charge Q0 is placed. Now according to the definition of electric field intensity, we know that electric field intensity E is equal to F by Q0, right, it is equal to F by Q0. Now F over here will be, if I consider this to be a small line element, as I told you dl, then according to this dl, how do we write it down? This dl will be dq by dl is equal to lambda, right. So dq is actually equal to lambda into dl, right, and therefore what is Q0? Q0 is the test charge. So you know the force will be nothing, force is according to the Coulomb's law, right, and therefore what expression we get over here is 1 upon 4 pi epsilon naught, right. Now I'll tell you just now, integral of dl length lambda into dl upon r square into r cap. Now r is the distance of this line element from Q0, right, r is the distance of the line element from Q0. So r is that particular distance. Now if I want to write down what is F between this dq amount of charge which is present in dl and Q0, you know it is according to Coulomb's law, F will be equal to 1 upon 4 pi epsilon naught, right, 1 upon 4 pi epsilon naught dq into Q0 upon r square, dq into Q0 upon r square. Now dq into Q0 upon r square is F. Now F upon Q0, Q0 and Q0 will get cancelled, and therefore you will be left with 1 upon 4 pi epsilon naught dq upon r square, and in terms of for dq I have written down dq is nothing but it is equal to lambda into dl. From here you can see that dq is nothing but dq is equal to lambda into dl. So that is what I have written over here, and the whole element, this is for the small element, but the whole element can be, the whole line of charge can be divided into very, very small elements, and therefore the total field due to the entire line of charge at the point Q0 will be nothing but the summation of that, and the summation is nothing but the integration, therefore integration of L lambda dl upon r square into r cap, and 1 upon 4 pi epsilon naught is the electrostatic force constant. So that is your electric field intensity at the location of the charge Q0 due to the entire line of charge, right. So we continue now. Next is surface charge distribution. Now when we talk about surface charge distribution, we are talking about that the charge is distributed over a surface. So as you can see, this is some surface S, okay, and the charge is distributed over the entire surface. So you can see that the charge is distributed over the entire surface, and we have taken to be a positive charge distribution. So the obviously the field will be directed away. Now as we are talking about surface charge distribution, we have considered a small surface element which we have denoted by ds. Now when we are talking about surface charge distribution, we talk about surface charge density, and surface charge density is charge per unit area. Now sigma is the symbol for surface charge density, and therefore this is equal to dq upon ds, right? That means small amount of charge which is present over this surface element which is ds, and that is dq, and from here you can write down dq is equal to sigma into ds. Similarly, what will be, just as I told you, linear charge density has the unit coulomb per meter. What will be the unit for surface charge density? It will be coulomb per meter square, because area is measured in terms of meter square and coulomb is the unit for charge. So coulomb per meter square. And what will be, how do we write down the expression for the electric field at q naught, at some location q where the charge q naught is placed, right, from the entire surface area, right? So that will be Es vector, because we are talking about surface, Fs vector upon q naught, 1 upon 4 pi epsilon naught, it is the electrostatic force constant. Now integral of S over here, right, integral of S sigma ds upon r square into r cap. Let me first show you how do we write it down from the small surface, let's say ds. So what will be E over there? E in that case will be equal to 1 upon 4 pi epsilon naught dq upon r square into r cap. So let me put a vector sign on E vector also, dq upon r square into r cap, where r vector is the distance between the surface element ds and q naught, right? So therefore this is the expression for E vector. Now if the whole surface is divided into small areas, area elements like ds, then we have to write down the summation of everything, and summation is nothing but integration. Therefore we have this expression 1 upon 4 pi epsilon naught integral of S sigma ds. Why sigma ds? Because dq is equal to sigma ds upon r square into r cap, right? So therefore we can write it down in terms of this, okay? So hence this is your electric field due to the surface charge distribution at the location of the charge q naught, okay? Similarly, we talk about volume charge distribution. Now volume charge distribution is that when the charge is distributed uniformly, uniform distribution of charge over a volume, that time we talk about volume charge distribution, and we define a term which is called volume charge density, denoted by rho, and this is equal to dq upon dv, right, dq upon dv. So what is dq over here? dq is equal to rho into dv. Now then again, this whole volume we can divide into small volume elements like dv, and therefore we write down the expression for the electric field due to volume charge distribution at the location of the charge q naught in the similar manner as what we have done just now for linear charge distribution and surface charge distribution. So again, you know, a formula for writing down electric field due to point charge is that 1 upon 4 pi epsilon naught q upon r square. Now here q is nothing but dq, because we are talking about the small volume element, and the distance of the charge q naught from this volume element we have considered it to be r vector. Therefore in this case E is equal to 1 upon 4 pi epsilon naught. If I am talking about due to the small volume element, this is equal to dq upon r square into r cap, right, okay? Now this dq, according to the definition of volume charge density, it is equal to rho into dv. So rho into dv. So therefore when I write this down, rho into dv, so I will get E vector is equal to 1 upon 4 pi epsilon naught rho into dV upon r square into r cap. I will get this. But if I have to write down due to the entire volume, then I have divided the whole volume into small volume elements, and I have to write down due to the entire volume, which I have over here. So in that case, the integral sign will come over the entire volume. 1 upon 4 pi epsilon naught will be outside the integral sign, integral over the entire volume, rho into dV upon r square into r cap. So this expression we get, right. So this is due to the volume charge distribution. Now then we move on further, and now we talk about what are electric field lines. Now this is a very important concept, electric field lines, and first of all it's a visual concept. As such, it means to say that this whole concept, it's an imaginary concept, you have to visualize it, and this concept was developed by Faraday, and it's a very excellent way of visualizing electric fields around a charge configurations, whether it's a discrete charges or whether there are continuous charge distributions. So we can visualize the electric field around a charge which we have. How do we define electric field, right? So the definition of electric field is given over here, and I'll explain you along with the diagram which I have on the slide. An electric field line is a path, straight or curved. It can be a straight path, it can be a curved path in electric field, such that tangent to it at any point gives the direction of the electric field intensity at that point. So electric field line, let us say it's a straight or a curved path. For example, AB is the electric field line which I am talking about, such that tangent to it at any point. Okay, so I take a point, let's say P over here, the tangent to it at any point. So tangent to the tangent at point P to the electric field line will be this particular tangent, right, this particular tangent. So this EP vector is the direction of the electric field intensity at the point P. Okay, so it's a field line. Field line is a path, straight or curved in electric field, such that tangent to it at any point gives the direction of the field intensity at the point. Suppose I take another point Q over here. Suppose I take another point Q. This is the point Q. Now at this point Q, what will be the tangent at the point Q to this field line? This will be the tangent, right? And I denote this tangent, let us say, by EQ vector, right? So this EQ vector is actually the direction of the field intensity at the point Q. So this is how we define it. It's a path, straight or curved in electric field, such that tangent to it at any point gives the direction of the field intensity at that particular point. It's also defined as the path along which a positive charge would move in an electric field or in an electrostatic field if free to do so, right. So if free to do so, it's the path along which a unit positive charge would tend to move. We'll continue further, and now we talk about important aspects related to field lines. Electric field lines due to an isolated positive point charge. They are directed radially outwards. Now what do we understand by isolated positive point charge? Isolated positive point charge means that there is a single charge which is positive and there is no other charge in its vicinity. There is no charge surrounding it. Okay, it's isolated. And the field lines, they are directed radially outwards, because what did we say just now? It's the path along which a unit positive charge would tend to move. So you know that if I place a unit, this is a positive charge. If I say that if I have a charge somewhere here right? A positive charge, if I have somewhere here, then you know there will be a force of repulsion and the positive charge would tend to move away from the positive charge, isolated positive charge which I have over here. So, and these field lines, they start from the charge and they end at infinity. So these are the field lines. Okay, similarly you can have the field lines from here. So anywhere you place the charge, they will be, the charge will be directed, the unit positive charge would be directed away. Okay, because there will be a force of repulsion. So similarly over here, if I have, they are all directed radially outwards. So this is how we say that they are directed radially outwards. So electric field lines due to an isolated positive point charge are directed radially outwards. In the question, it can even be given as, instead of writing isolated positive point charge, they can say that Q greater than 0. Q greater than 0 means it's a positive point charge. You should know this, right? Similarly, if I talk about electric field lines due to an isolated negative point charge, they are directed radially inwards. Why will they be directed radially inwards? Because if I place, if this is the negative charge, isolated negative point charge, it is also a path, field line is also a path along which a unit positive charge would tend to move. So if I place a unit positive charge over here, then what will happen? There will be a force of attraction because this is negative, and if I place a unit positive charge here, let's say Q naught, so there will be a force of attraction and the direction of this will be nothing but towards the charge. So that is why they are directed radially inwards. So you can show, and these, they will start from infinity and they end at the charge. Okay, and you must remember a few things, the properties which I will tell you after this slide, that what we have to be careful about. You should not start two lines of force from the same point, which is wrong. And secondly, these should be straight lines, they should not be curved. Okay, if you are drawing something like this, this is a positive charge, right? If you are drawing something like this, then it is wrong. It is wrong. This is a wrong way of depiction of field lines due to an isolated positive point charge. अगर आप इनको bend कर देते हैं, if you are bending them, right, then it shows that there is some other charge in its vicinity because of which the field lines are going in this manner. So this is a wrong way of depiction of isolated field lines due to an isolated positive point charge. You should not be doing it in this manner. Okay, similarly, due to an isolated negative point charge also, you should be drawing straight lines and they are directed radially inwards. They start from infinity and end at the negative charge. Then the lines due to a pair of equal and opposite charges, right, show mutual attraction between the opposite charges. So over here, these are two equal and opposite charges. There is a positive charge, there is a negative charge. So you can see that the charges, this is positive, this is negative. The field lines, they will start from the positive charge and end on the negative charge. But no two field lines are starting from the same point. You got to understand this. I'll be doing it in the properties also. And the field lines which have been shown over here, they are showing mutual attraction between the opposite charges. So you must know how to draw this. You must learn this particular diagram because it comes in the exam. This is positive, this is negative. The field lines are starting from the positive charge, ending at the negative charge. So यहाँ पर you are showing it in this manner. It doesn't mean that there is a break. We haven't shown it because of the you require more space to draw the diagram. Otherwise, it continues and it goes like this, right? This is how it will go. Okay. Similarly, on this side also it will go in this particular manner. तो ये यहाँ पे break नहीं है. That is continuous only. It is not breaking over here. We haven't shown it because of the lack of space. Otherwise, they will go like this. Okay. right. So that's how it is. They will start at the positive charge, end at the negative charge. So यहाँ से start हुआ and it ends at the negative charge, right. But they do not go within the charged conductor. That I will tell you in the properties. Now electric field lines, it is continued again. So here you have electric field lines due to two equal positive point charges. So here you have two equal positive point charges. So this is plus Q1, this is plus Q2, right. There are two charges. This is also positive charge and this is also positive charge. They are both equal, right. They are both equal. Q1 and Q2, Q1 is equal to Q2. So here you will see that this particular diagram is showing that they are exerting lateral pressure on each other because they are showing repulsion between like charges. So the field lines will go like this, and this is a positive charge, so the field lines will be directed away, right. This is a positive charge, the field lines will be directed away like this. Yeah, they have to be shown in this particular manner. And you know, in the region between the two charges, there will be a particular region where the field lines are not there. So you can see that there are no field lines between this particular region, right. There are no field lines in this region. And in the line joining the centers of the two charges, there is a particular point P where the electric field is 0. The electric field intensity is 0 at the point P. So at the point P, the electric field intensity is 0. Now the second case over here is when the charges are unequal. In this particular case, Q1 is equal to Q2. So in the line joining the centers of the two charges, there is a point P where in the midpoint, there is a point P at the midpoint of the line joining the centers of the two charges where the field intensity is 0. When the charges are unequal, that is Q1 is not equal to Q2, and let us say that Q1 is greater than Q2. In this particular case, when Q1 is greater than Q2, your field lines will again be directed, they will be exerting lateral pressure on each other because of repulsion. But the point P over here, the point P, which was where the electric field intensity is 0, it will shift towards the smaller charge. The point P will shift towards the smaller charge. So in this particular case, the line which is this dotted line is the line joining Q1 and Q2. So the point P will not be at the midpoint as Q1 is not equal to Q2. It will not be at the midpoint, but the point P where the field intensity is 0, electric field intensity is 0, it will shift towards the smaller charge. Okay, so that's what how we explain this. Now we come on to the properties. We say electric field lines are discontinuous curves. Discontinuous curves, you should understand that they are not existing within the charged body. They will start from the positive charge and end on the negative charge. They will not go within the charged body. That is why they are said to be discontinuous curves. They start from a positively charged body and end at a negatively charged body. These lines are not existing inside the charged body, right? And they are not forming closed loops, right? So closed loops nahi hai. They are not forming closed loops. They are going from the positive, ending on the negative charge. But they are not going from negative to positive again. Okay, that is not happening, right? So that is why we are saying that they are not forming closed loops. Then electric field lines contract longitudinally on account of attraction between unlike charges. So this property is also explained on the basis of this particular diagram only, that they are contracting longitudinally on account of attraction. Now why are the lines of force going in this particular manner? Why are they bending and going in this particular manner? Because there is a force of attraction between the positive charge and the negative charge. That is why they are contracting longitudinally on account of attraction between the two charges, unlike charges. Thirdly, Tangent to the field line at any point gives the direction of the field intensity at that particular point. This particular property is already explained to you when we had discussed about just now about the definition of electric field line, right. So, tangent to the electric field line at any point gives the direction of the field intensity at that point. So, suppose this is your electric field line AB, right. So, at this particular point, if I draw the tangent at the point at this particular point P, then this EP vector gives us the direction of the field intensity at the point P. So, this I have already explained it to you. Electric field lines are always normal to the surface of the conductor while starting or ending on the conductor. So, electric field lines, they are always perpendicular to the surface of the conductor, right. They are always perpendicular to the surface of the conductor when they are starting or ending on the conductor. That means when they start from the positive charge and end on the negative charge, they are always perpendicular or normal to the surface of the conductor. So, this is the fourth important property. Then electric field lines exert a lateral pressure on account of repulsion between like charges. This I have already explained it to you with the help of the diagram which we have done a previous slide also, that electric field lines, they exert a lateral pressure on account of repulsion between the like charges. This is Q1 is equal to Q2, they are both, let us say, positive charges. So, you can see that the field lines are going away from the charges and they are exerting a lateral pressure, right, because there will be repulsion between Q1 and Q2. Then density of field lines is more near the charge and hence E vector is strong in that region. Suppose I take the help of this particular diagram, or I take the help of this diagram also, you can see that the density of field lines is more near the charge, and as we go away from the charge, the field lines are the distance between the field lines go on increasing, right. The distance between the field lines go on increasing. So, hence when the density is more in a particular region, electric field is strong in this particular region. So, as clearly it depicts, electric field will be strong in this particular region near the charge, and as we move away from the charge, right, as we go on moving away from the charge, electric field lines, the density of the field lines will become smaller and electric field will become weaker and weaker. So, the density of the field lines is more near the charge and hence electric field is strong in that region. Density of field lines is smaller from the charge and hence electric field is weak in that particular region. Then two lines of force can never intersect each other, right. This is a very, very important property and it is usually asked in the exam. Two lines of force do not intersect each other, right, because if I say that the two lines of force are intersecting, okay, suppose I say that the two lines of force are intersecting at this particular point P, then this is one line of force and this is another line of force. So, let us say this is 1 and this is 2. So, at this particular one line of force, then at this point P there will be this particular tangent drawn, that is E1 vector, and due to this particular line of force at the point P there will be another tangent drawn, that is your E2 vector, right. Now, at this one point P, there are two directions of field intensity. There are two different directions of field intensity which is not possible, At one particular point, you can only have one particular direction of field intensity. You cannot have two different directions of field intensity. So, that is not possible. Okay. So, hence two lines of force can never intersect each other. Therefore, I told you previously also that when you are drawing the field lines, you should not start from a single point only. You should start from the different points only to draw the field lines. Okay. Have you understood? Okay. So, um, this is what I wanted to tell you about the electric field lines and its properties. If you want to see more such videos, hit the subscribe button and like and share the video. Thank you. Thank you.